Good afternoon, everyone. My name is Ziqiang Cao from Peking University. Here I will illustrate our work named Joint Learning of Chinese Words, Terms, and Keywords. At first, let me introduce these three concepts. Unlike English, Chinese does not delimit words by white spaces. Therefore, Chinese word segmentation is the most fundamental step followed by other tasks, including term extraction and keyword extraction. Terms are the identification of a domain, while keywords summarize a document. Simplified for Chinese, they can be regarded as words frequently appear only in a domain or document. We can see the three items lie in different text levels. Words are associated with the whole corpus, terms a domain, and keywords a document. Most websites have the corpus to domain to document structure and requires all the three tasks. An example is given here. This sentence is from a document concerning heparinoid in the disease domain. Therefore, heparinoid is the keyword for this document, while thrombocytopenia, a kind of disease, is mentioned by many documents and can be treated as a term. We use different colors to highlight the role of a word. Blue means a term and red stands for a keyword. Previous work often use a pipeline framework, where Chinese word segmentation is followed by TE and KE. Such framework suffers from error propagation and is unable to leverage information in later modules for prior components. For instance, the segmentation result with the state-of-the-art CRF approach is shown here. As can be seen, thrombocytopenia is segmented into three common Chinese words, and heparinoid is mixed with its neighbors. Through the recombining step of term extraction and keyword extraction, the former may be repaired, whereas the latter mistake always remains. HDP is a non-parametric Bayesian approach to model the diversity and commonality in multiple correlated corpora. It consists of two derived processes. The second process, G2, takes the first process G1 as its basic measurement, and the two alphas are the concentration factors. HDP has been used for word segmentation by Goldwater. Goldwater's approach can be viewed as a background language model with a uniform backoff. Here, G0 is the prior word distribution, G1 is the uniform distribution, while HW, the background distribution specially to word W. With the language model, word segmentation is implemented by a character-based Gibbs sampler, which repeatedly samples the possible word boundary positions between two neighboring words, conditioned on the current values of all other words. However, Goldwater's model can be deemed as modeling the whole corpus only. Back to our problem, it is noted that word segmentation, term extraction, and keyword extraction can be made consistently. To be specific, each of them is associated with a word distribution but stays on different text levels: words, corpus level; terms, domain level; and keywords, document level. To jointly learn the word information from various levels, we extend Goldwater's model by adding two levels of DPs, and we named our model DP4. The whole model and the generation process is shown in this figure. We use M to indicate a domain and MJ to represent a document in this domain. The first three items, G0, G1, and HW, have the same meaning as Goldwater's. Then comes the domain background distribution, followed by the document background distribution. While HWM is generated according to the standard DP, the background distribution of one document depends on both the background distribution of this domain and other documents in the same domain. We want similar documents to exhibit similar background distribution since most documents are quite short. Here we provide for our model the Chinese restaurant process metaphor, which can create a partition of items into groups. Current word WI corresponds to a restaurant. Previous word WI-1 is related to a restaurant. A domain is analogous to a floor in a restaurant, and a document is denoted by a room on this floor. Previous customers enter a specific room on a floor of a restaurant and seat themselves at a table with the label of a word type. Different from the standard HDP, each customer sits at an occupied table with a probability proportional to both the numbers of customers already seated there and the numbers of customers with the same word type seated in the neighboring rooms. Now we present the detailed inference formulas. Originally, it is important to build an accurate G0, which determines the prior word distribution. We consider the dependence between characters and use the string frequency statistics. Then, with the CRP metaphor, we can obtain the expected word unigram and the background distributions on the corpus level related to G1 and HW. Also, we can easily get the background distribution on the domain level by extending to the third DP. To model the background distributions on the document level, it is beneficial to consider the influence of related documents in the same domain. Here, we only consider the influence from the k most similar documents with the simple similarity metric S, which calculates the Chinese character overlap ratio of two documents. We use T, here T, to replace N in the DP formula, so that a document seems to be lengthed by its neighbors. With CRP, we can also easily estimate the unigram probabilities on the domain and the document levels through combining all the restaurants. To measure whether a word is eligible to be a term or a keyword, we use these two score functions. They can extract the words which only frequently appear in a domain or document. The character-based JIP sampling for word segmentation is extremely slow to converge. You introduce the sentence-wise JIP sampling technique as well as an efficient dynamic programming strategy. The basic idea is that we randomly select a sentence in each sampling process and use the VTB algorithm to find the optimal segmentation results according to the word distribution derived from other sentences. TE and KE can speed up this step. Once a word is identified as a term or keyword, it will drop out of the following sampling. Its CRP explanation is that some customers find their proper tables and keep sitting there afterwards. Now let's move to the experimental section. It is indeed difficult to find a standard evaluation corpus for our joint tasks, especially in different domains. As a result, we spent a lot of time to collect and annotate a new corpus, which consists of 10 domains, namely physics, computer, agriculture, sports, environment, history, art, politics, economy, and disease. The basic information of our test corpus is listed here. In addition, there exists a large amount of manually checked segmented text for the general domain, which can be used as training data for further segmentation. Like other non-parametric Bayesian models, DP4 can be easily extended to semi-supervised learning by imposing the word distribution of the segmented text on the corpus level. Therefore, we adopt the PKU corpus, a widely used segmentation data, as the extra training set. 4 baselines are implemented for comparison with segmentation results, namely forward maximum match, reverse maximum matching, conditional random fields, and HDP-based semi-supervised approach. All these methods adopt the PKU corpus as training set. Then, the segmentation result of each approach is used for further extracting terms and keywords. We employ the same score functions as DP4s. Additionally, we compute mutual information to identify the candidate terms or keywords composed of more than 2 segmented words. As for our model, this recognition process has been done implicitly during sampling. The metrics of F1 and the out-of-vocabulary recall are used to evaluate the segmentation results, referring to the gold standard. To evaluate the TE and KE performance, the top 50 and 100 accuracy are measured for the identified terms of one domain, while the top 5 and 10 accuracy for the keywords in one document. This table demonstrates the result averaged on 10 domains. In terms of segmentation, our model significantly outperforms FM, IMM, and HDP, and witnesses a slight advantage over the CIF. We check our segmentation results and find that the performance of DP4 is depressed by the identified terms and keywords, which may be composed of more than 2 words in the golden standard. For example, data interface is a term and DP4 regards it as a whole, but the gold standard segments it. As for term extraction and keyword extraction, our model performs significantly better than all the other methods. In conclusion, we propose a 4-level DP-based model to construct the word distribution from the corpus, domain, and document levels simultaneously, through which Chinese words, terms, and keywords can be learned jointly and effectively. In the future, we plan to explore how to combine more features in our model. That's all. Thank you.
So we have plenty of time for questions. Any questions? More questions? So I do have questions. So when you present results, kind of so I need some clarification and also a question. So one of the competing methods here in the baseline is the CRF method. Okay, so I don't get it clear.
Which one?
Yeah, and the results. So here you have CRF. So I have a conditional random field here to compare results. So it is not clear to me how do you extract the terms and the keywords in this case of the CRFs.
Yeah,
CRFs are trained with the PKU corpus.
Yes.
And so I see that for the segmentation task, the quality is almost comparable to the DP4 method you are proposing. However, when you go into the detection of terms and keywords, the difference is clearly in favor of the DP method, right? So how can it be that there's this large difference in the extraction of terms and keywords when the segmentation is almost the same? That was my question. Where does this advantage come from?
Maybe they have mistake in different words. CF may be segmented more rightwards for general, and our model segmented terms and keywords more rightly. I think this results CRF and DP4 in segmentation. They are the same. They are similar, but for T and K they have a difference.
Okay, so you're suggesting that maybe the F1 result is very similar, but the actual segmentation is quite different?
Yeah.
And the one that you are proposing is more oriented to the term and keyword extraction because the processes are performed together, jointly.
Yeah.
So I also wanted to ask, since you have 10 different domains, here we are presenting the results for an average of all domains.
Yeah.
So did you observe similar results across all domains, or there are many differences among them?
Yeah, we have a table show all the results, but I only listed the average one.
Yeah, I understand that for brevity reasons in the paper and here for the space, you cannot show everything, but any comment on, so are the results obtained in every domain similar to each other?
Yes.
So are these conclusions only the average, or they are stable across domains?
Yeah, I think we will present it more clear.
Okay. So more questions? It's time?
Yes.
No, it's not time. Okay. Still have 2 minutes. We started a bit late. Okay. Okay, no more questions. Thank you very much again.